Hi guys, today's lesson is over 5.3, which is called graphing cubic functions. Okay, so basically today what we're going to do is we are going to learn about the cubic function specifically. Okay, so a cubic function is a function that is to the third power. Okay, so in the last section that we were working on, we did quadratic stuff. Okay, so today we're going to be specifically working on just cubics. Okay, hopefully what you see right here looks slightly familiar to you. This right here is the form that we're going to be working in for this particular lesson. Okay, so we have this one right here and this one right here. I'm just going to go ahead and combine this. So we're going to call this vertex form of a cubic function. Okay, so it goes f of x is equal to, and then we have the a times 1 over b x minus h cubed plus k. So this should look familiar. We did this exact same form when we were working with quadratic functions. Okay, so we basically are taking these functions and we are doing the same transformations that we did before. Okay, so let's see if you can remember what direction all of these things do. Okay, we've talked about this in the past. Okay, so pretend if this was a 2, if we were working with a quadratic, these transformations would hold true for our cubic. Okay, so if we have the k out here, if something is added or subtracted to our function, what direction does it move? Okay, so hopefully you said up or down. Okay, for it to go up, you would need a positive value. For it to go down, you would need a negative value. Okay, so if you had a minus at the end. Okay, the k, or excuse me, the h, is now your left and right movement. Okay, so if I'm going to go left, that is going to be a positive. Okay, so you'd have like x plus 2, and that would go to the left 2. Or if you were going to go to the right, you would end up having a subtraction sign there. Okay, so that's kind of opposite of what you would think. Okay, now if you're looking at the two numbers that are in the front, okay, we did work with these a little bit. We didn't work with the b as much, but we did a little bit when we were working with the transformations of functions. So let's see if you can remember. The a does what? How does that affect the function? Okay, the a is your vertical stretch or compression. Okay, so for it to stretch, we'd have an a value that would be greater than 1, so such as 2 or 5, versus a compression, okay, which is going to squish it towards the x-axis. And that would be some kind of value that would be a fraction, okay, which means it would have to exist between 0 and 1. Okay, for the b value, this is going to be basically the exact same, but instead of vertical, we have horizontal. Okay, so for a horizontal stretch, the a has to go between 0, or excuse me, this is going to be the b, 0 and 1. Okay, so again, when it's on the inside of the parentheses, it kind of works opposite than what your brain would think. Okay, as opposed to the compression horizontally is going to have to be a b value that's greater than 1. Okay, so these are all of your transformations, and this is going to work for basically any function. Okay, and this is going to work for whatever. We've also talked about reflections. Okay, so remember If we have a negative in front, okay, that's going to reflect over which axis? Over the x-axis. Good. Okay, and if the negative is inside the parentheses, that one's going to reflect over the y-axis. Whoops. Okay, so these are all your transformations that are going to hold true for a cubic. Okay, so at this point, we now need to know what a cubic function looks like. Okay, so let's talk about simply the parent function. Okay, so basically a parent function is the most basic function where there's no adding, subtracting, multiplying, or dividing. There's just simply an x, and it is simply cubed. Okay, so the most basic parent function for a cubic is x cubed. Okay, so we want to know what an x cubed function looks like. Okay, we've seen f of x equals x. That looks like a linear function. We've seen absolute value. That looks like v's, and we've seen parabolas, which are x squareds. So now, working with a cubic function, let's go ahead and use Desmos and kind of have it do the hard work for us. Okay, so we have x to the third. Okay, so this is a cubic function. Okay, so basically, we can say that, here, let's take a screen pic of this and let's talk about pieces that are important. Let's kind of throw this in here. There we go. Whoa. Let's try to make this smaller real quick. All right, there we go. So the first thing that I need to do to this function is I need to give it a name. Okay, so it doesn't actually have a technical name, but of course I need to have a name for it. So I call this the John Travolta. And I'll tell you why I call it the John Travolta. If you've ever seen an incredibly old movie called Saturday Night Fever. Oops, not live. That's a different show. Fever. Saturday Night Fever is a movie about disco dancing. So, I'm not sure if you can see the relation that I see here. If you took a picture of this and threw it up over here, do you kind of see, like, if you were going to kind of become this cubic function, how you would kind of look like this John Travolta, okay, where he has a disco dancing style, okay, like, there he is. There's his two arms, one's going up, one's going down. There's John Travolta. So that's why I call it the John Travolta, just so you know. Let's see if we can get this out. Okay. So the pieces that are important about this function. Okay, so let me erase my little picture. We needed to know what the domain is, what the range is, what the end behavior of this function is, so that we understand it fully. Okay, so if we talk about the domain of this function, hopefully you remember that the domain is all of the x values. Okay, so if you're thinking from left to right, remember that this function does go infinitely in both directions. Does this have any restrictions? Okay, and it does not have any restrictions. So the domain is going to be all real, so it's going to exist from negative infinity to positive infinity. There's no restrictions. Okay, if you look at the range, okay, the range is the y values. Okay, so you're going from the lowest value to the highest value. The lowest value that this function will hit is eventually negative infinity, and it will eventually go up to positive infinity. So again, the range is the same as the domain. It's going to go from negative infinity to positive infinity. If we talk about the end behavior, okay, where are these two ends going? Okay, if you look at this right end, let me go back to Desmos. Okay, so as x approaches infinity, okay, we're looking way over here. It's hard to imagine, but as x goes to infinity, as it gets bigger and bigger and bigger, what is the y value approaching? Okay, so the y value is going up, 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 up. Okay, going to infinity. So we can say as x approaches infinity, the y value, which we're going to call f of x, the y value approaches infinity. Okay, and we can also say as x approaches negative infinity, okay, so now you're looking at his left end, so looking down, as x goes farther and farther to the left, what is the y value doing? Where is that function going? Okay, it's going down to negative infinity. So the y value is going down to negative infinity. So that's our end behavior. So the thing that's kind of cool about these John Travolta functions is that the domain and the range is always going to stay the same. It doesn't have any max or min, so we don't ever have to find a vertex specifically. Same thing with the end behavior. It's going to always go up or it's going to go down. So the only way you could change it is if you flipped it upside down, and if you had a negative in front, imagine it being flipped upside down. Okay, then you're looking at this right arm gets turned and goes down, and the left arm goes up. Okay, all right, so now that we know what we're working with, let's go ahead and do an example of graphing. Okay, so here's an example for graphing. Okay, we're gonna do, oops, see if I can pull this over. There we go. We'll just pull this right here. Okay, and so all you're gonna be asked to do is to just to graph this. Okay, so in order for you to graph this, okay, the same things are needed, okay, as what I asked you for the parabola. Okay, I would like you to list the vertex, and when I say the vertex, I'm putting this in quotes, because a vertex by definition is kind of like the max or min of the parabola. The vertex of John Travolta is just kind of that center point. Okay, so kind of where John Travolta's head would sit on top of his body. Okay, so that's going to be our reference point. Okay, so if we take a look at this, what are the two translations that this John Travolta moves? Okay, if I have a -1, what direction is that going? Okay, hopefully you said down 1. Okay, if we have -1 on the inside, what direction does that go? That goes to the right one. So right one. Okay, and then up front, this is going to affect our a value, okay, which we're going to refer to as the slope. So I'm going to say m is equal to 2. Okay, and even though I'm using the word slope, we all understand that that's just a reference idea to come up with our 2 additional points. All right, so we're going to graph our little vertex. Okay, so it goes down 1 and to the right 1. So right here, at this point, our vertex is -1. Okay, and then I need 2 additional points. Okay, and I want to label these, and I'm going to use the slope. Okay, so remember I have to draw this John Travolta with his right arm up. Okay, has a slope of 2. So if I go up 2 and over 1, up 2 over 1, That's going to be one place where it's going to go through. And now to get to this left arm that's down, I need to go down 2 and over 1. Okay, now it looks like I have 3 dots that are right in a row, okay, like a straight line, but remember that I'm drawing a John Travolta. Okay, so I'm going to come steep up, it's going to do its little bendy, and then it's going to come up. Okay, so actually let me see if I can draw that a little bit better. Let's use a different color. So something like, there we go, looks a little bit better. Okay, and if you want, you can throw that back into Desmos, or you can put it into a graphing calculator and just see if what you have is correct. So if I have 2, whoops, I need parentheses, x minus 1 to the 3rd, and then minus 1. Okay, so I should be able to find those exact same points that I found. Okay, so I have, let's see if I can trace this. So there's my vertex, and this is kind of zoomed in a little too far. There we go, that looks a little better. Let's see if we can get it. There's my vertex, 1, -1. Let's see if we can get it. Ooh. There it is. Okay, and then we found our second point as 2, 1. Saw it? Oop. And our other point was 0, -3. Okay, so make sure to, again, label your points. We want to make sure we're not just kind of saying, oh, this looks like about a point. It looks good. That. Okay, so just identify exactly what your points are. Whoops, 0, -3. Okay, nice. Okay, so let's do one more. Just make sure that we do have this. Let's do one. Yeah, I like this one. This is a good one. Okay, so we're basically doing the exact same thing. Whoops, missed. Struggling with my stylus here. No, it's not letting me take a picture. Okay, I'll just have to write this down. So we're going to graph, this will be example 2, g of x, they call this one -1/2 x minus 3. Okay, so again, we're just graphing, okay, so I would like for you to list the vertex and then the 2 additional points to do this. Okay, so first we're going to talk about the translation. So if I have a -3 inside the parentheses, what direction is that moving? Okay, so we have a movement to the right 3. Okay, this -1/2. The negative does something, and the the 1/2 does something. So the negative, we have a reflection over the x axis, and then the 1/2 is our slope. Okay, now this is a little bit tricky on this one because you have a fraction, and when you do slope with polynomials that are not linear, you can't just go up 1/2. Okay, and we did do this with our parabolas a little bit. So let me just explain this. 2, 3. So we have it moved to the right 3. So our vertex is exactly right at 3, 0. Okay, so now I know that it's going to be reflected. So I know that I'm going to have this left arm up, right arm down scenario with a fraction of 1/2 as my slope. Okay, so the slope is always going to be 1 unit horizontally. Okay, so what this really is 1/2 is my rise, and my run is always 1. Always. From the vertex. Must be. Okay, otherwise this isn't going to work. Okay, so that means if I'm going to draw my John Travolta with his left arm down, I'm going to have to go down 1/2 and over 1. Okay, so here, let me move this label. It's kind of in the way. We'll say V, 3, 0, our vertex. Okay, so this point right here is going to be 4, -1/2. Okay, if I want to draw his right arm, or excuse me, his left arm up, I'm going to go up 1/2 to the left 1. So this point right here is going to exist at 2 and 1/2. Okay, so now when I draw this John Travolta, it's going to be a little bit wider than the normal John Travolta. Okay, and again, you can check that on Desmos if you want. Make sure that we are getting those same points. Okay, so we have negative 1/2 to the 3rd. Okay, so there's the vertex, and then you can see that the slope is right here at 4. Let's see if I can get it. 4 and negative 1/2. There it was. Okay, so it's not down 1/2. You see how that's not right? Down 1/2 would not be on our function. Okay, so be really careful about that slope idea when they're fractions. Okay, so hopefully we're all right with this. Let's see. Here's the last thing that they ask you to do. So what they're going to do in this scenario is they're going to give us the function drawn as the graph and ask us to write its equation. Okay, so let's see if I can get this going this time. Nope, still won't let me. Try it one more time. No, okay. All right, so let's see if I'll just zoom in over here. Okay, so what they want me to do is they want me to write the equation of this cubic function. Okay, and they gave us the model as a times x minus h cubed. Now, they might not always give you this model. Okay, so I will tell you that I want you to always start with this model no matter what is given. If they say maybe it's this one instead, go ahead and just use this one and don't ever use this B one. Okay, just always use the A value one. Okay, so here is our general form, and we basically need to fill in all the pieces that we can. We need to fill in the A, we need to fill in the H, and we need to fill in the K. Okay, so if you look at this graph, this John Travolta, we need to first find the vertex. Remember, that's our vertex. Okay, so our vertex is this point right here in the middle where it wiggles. So -2, -2 is our vertex. So that means my H value is -2, my K value is -2. So for my equation, I have A times X minus -2. So if I have minus a negative, that's the same as plus Q, and then -2 for my H. So at this point, I'm almost here. I'm still missing the A. Okay, so now what I'm going to do is I'm going to use the idea of the slope. Okay, so there's two ways to do this. If the slope that they give to you is 1 horizontal distance away, we can immediately fill in what the A value is. Okay, so this one is actually a rise of 1, 2, 3 over 1. So I can say my A value is 3. Now if it's not 1 horizontal distance away, what I'm going to have to do is use a point as an X and a Y and then solve for the A value. So that's what I'm going to do here so you can see it, so you know how to do it if they don't have that on the worksheet. Okay, so it doesn't matter which of these 2 points you use. Okay, I'm going to use the nicer of the two, so I'm going to use that point. Okay, so remember that this is X and Y. So that means my X value is -1, my Y value is 1. So what I'm going to do is I'm going to plug these into this equation. So my X value is going to be -1, and my Y, which is a fancy way of saying g of X, right, is that one. Okay, so let's go. 1 equals A, my X value is -1 plus 2 cubed minus 2. So now I have this equation that I can solve and solve for the A. So my first step in doing this is to get rid of anything that's added or subtracted. So first thing I want to add 2. So 1 plus 2 is 3. And then on my next step, I can go ahead and simplify the parentheses that has been cubed. So -1 plus 2 is 1, and 1 to the 3rd power is 1. So now my last step to solve for A is divide by 1. So we can actually conclude and prove that the A value is in fact 3. So the equation for this John Travolta up above is 3 times the quantity x plus 2 cubed minus 2. Okay, so just to do that one more time here, just so you can see that, I'll do this example. Okay, and again, we're not going to use this version. We're going to do a times x minus h cubed plus k. Okay, so for this one, my vertex is the middle piece, so this right here is my vertex. Okay, so I found my h to be 1 and my k is negative 1. So if I plug that in, I would have a times x minus the h of 1, and then my k is minus 1. Okay, so now again I'm missing my a, and I can't use my quick slope idea because this is not one horizontal unit away. So I'm going to use a point, and I'm going to go ahead and use this point as my x and y. Okay, so my x value is 5, my y value is 0, so I'm going to plug 5 into the x and 0 into the y, or my g of x. Okay, so it's going to go 0 equals a times 5 minus 1 cubed minus 1. So now I have this equation with one variable and I can solve. So what's my first step? I'm going to add 1, and 0 plus 1 is 1. I'm going to simplify the inside of the parentheses, so I have 5 minus 1, which is 4, and 4 cubed. Ooh, 4 cubed is 64. And now I'm going to divide by 64. Wow. So for this one, my a value is 1/64. Okay. So my equation, now if I fill that in, my a value is 1/64 x minus 1 cubed minus 1. So I'm just pulling that straight down and filling in the a value. All right, so that should get you there through this lesson. I will see you soon.